Hi, in the previous module, we looked at modeling using CSPs. This module, I'm going to start talking about inference, in particular, introducing backtracking with dynamic order. So just a quick refresher, remember a CSP is defined by a factor graph which has a set of variables, n, where each variable on some values in domain of I. And it also has some factors, f1 through fm, where each factor, fj, is a function that takes a subset of the variables and returns a non-negative quantity. So the assignment weight is defined as follows. So each assignment to all the variables has a weight which is given by the product of all of the factors. And the goal in finding this, in solving a CSP, is to compute the maximum weight assignment. So let's start with backtracking search, which we already talked about a little bit. So the backtracking search is going to be the kind of blueprint for the current algorithm that we're going to talk about. So if we start with empty assignment, no variable has any colors, and we choose one of the variables, assign of a particular value, red in this case, and then we recurse, and we pick another variable, assign a value, and on recursing, so maybe we leaf, and then we back up, backtrack, and try green, backtrack, try blue, and then we backtrack up here. Now we're going to try setting WA to green. Down here, explore this subtree, then we come back up, explore NT green, NT blue, and so on and so forth. So at the bottom of this tree, we have the leaves, and each leaf is a complete assignment, and each assignment has a weight, which we can compute. And now, once we search through all the assignments, we simply take the assignment with the max. So this is the most straightforward way of taking a CSP and solving it using backtracking search. So the first thing we'll note is that we can actually compute weight of partial assignments as we go, rather than waiting until the very end to compute the weight of an entire assignment. So this is how it's going to proceed. So let's start with the empty assignment, and we assign WA red, and we can't evaluate any of the factors so far. But once we assign NT, we can actually evaluate this factor and test whether WA is not equal to NT. So these other factors we can't evaluate yet because we don't know these values, but values to these variables, but we can move on. Now we recurse, we assign SA value, and now we can evaluate these factors, W not equal to SA and NT not equal to. And we assign Q, we can evaluate these two factors. Assign NSW, we can evaluate these two factors. And assign V, we can now evaluate these two factors. And these are all the factors in CSP. So at any point in time, for example, at NSW, we have this partial assignment here, and we define the weight of that partial assignment to be the product of all the factors that we can evaluate, where all the factors are evaluable if all the variables in the scope of that factor have been set. So more formally, suppose we have a partial assignment, and it applies as follows. We're going to define the set of dependent factors as follows. So D of a partial assignment X and a particular variable Xi is the set of factors depending on Xi and X, but not on the unassigned variable. So for example, d of this partial assignment up here and this variable sa are simply these two factors here. These are the factors that are going to be multiplied in when xi is set. Okay, so now we're ready to present our main backtracking search algorithm. Okay, so this is going to be a kind of general blueprint for many of the bells and whistles that we're going to talk about soon. So backtrack takes a partial assignment x, and the weight of that partial assignment, which is all the factors that we can evaluate so far, and domains which specifies valid possible values for each of the variables in the CSP. More on this in a bit. So if x is a complete assignment, then we have reached the leaf, and we look at its weight, and we update our current best, and we return. If not, we're going to choose an unassigned variable xi. We're going to look at the values in the domain I of xi and order them somehow. We're going to go through each value in that order, and we're going to compute a weight update. So we're going to look at this assignment, which is the x extended with xi set to v. And then we're going to look at all the factors in the dependent set of factors of x, the partial assignment, and new variable xi that we're going to assign. Multiply all the factors evaluated at this extended assignment. So that number we're going to call delta, which is going to be the update on w. Okay. So if delta equals 0, then we stop there and don't recurse farther. Because remember, any 0 by a factor is enough to zero out the weight of the given assignment. So if not, then we continue. We're going to do this thing called Lookahead, which takes the domains and tries to reduce them, tries to prune away things based on this new assignment xi2. So now, if any of these domains become empty, then we can again prune and stop recursing. Otherwise, we're going to recurse and backtrack on this extended assignment with this updated weight w times delta and the new domains that we've computed. Okay, so this recipe has 3 choice points: how to choose the unassigned variable, how to order the values of the unassigned variable, and finally this lookahead, which is how we prune the domain. So we're going to talk about each of these in turn, starting with the lookahead. So we're going to introduce a simple form of lookahead called forward checking. Okay, so first we're going to visualize the domains of each of the variables with this set of valid colors above the respective. So in the empty assignment, all the values are allowed. Okay, so now we're going to set, let's say, WA equals red. So at this point, 2 things happen. First, we wipe out all the other values from that variable, which is clear. Set WA, we're committing to that. But in addition, what we're going to do is do one-step lookahead, forward checking. So we're going to eliminate the inconsistent values from the domains of xi's neighbors. So in this case, we're going to look at the neighbors of WA, which are NT and SA, and we're going to remove red from those domains. And why is that? Because this factor says that, well, if this is red, then this can't be red. So red is gone now. Okay, so now backtracking search is going to recurse, and it's going to, let's say it sets NT to green. So now, again, I do one-step lookahead, look at the neighbors of NT, and I'm going to wipe out green from these. Okay, so suppose I recurse again, and now I set Q to be blue. So again, one step look ahead. I'm going to wipe out blue from my neighbors. Now look what happens. SA has an empty domain, which means that there are no possible values that I can set SA to make the assignment consistent. So when, in this case, if any domain becomes empty, I simply return here. And this is important because now all of these other variables have not been set yet. And rather than recursing and trying to set them all sorts of different ways, I already know at this point that SA is not settable. So I just stop there. So this allows, forward checking allows me to use these domains to prune. Okay, so forward checking is also going to allow me to choose an unassigned variable and order the values in a variable. I'll show follows. So suppose we're in this situation. So WA and NT have been set, and I've applied forward checking to propagate the constraints to all the neighbors. So now the question is, which variable do I assign next? So there is this heuristic called most constrained variable, MCV, which simply chooses the variable that has the smallest domain. Okay, so what's the domain size here? So there's 2 elements of Q, 3 elements here, 1 element here. So SA is the variable that has the smallest domain. It has only 1 element. And the intuition here is I want to restrict the branching factor and choose variables that have small branching determined by the number of elements in that domain. So the second choice point is, once I've selected a variable, how do I order the values to explore? So consider the following. So I'm trying to assign a value to Q. Do I first try red or do I try blue? So the idea behind this heuristic called least constrained value is I'm going to order the values of the selected xi by decreasing number of consistent values of neighboring variables. Okay, so what does this mean on this example? So I look at Q, and remember I set this to red tentatively, and I propagate via forward checking to its neighbor. So I wiped out red here. And now I look at the neighbors and say, how many possible consistent values are there? So there are 2 plus 2 plus 2. So that's 6 consistent values. And what about if I set it to blue here? And I've eliminated blue from these neighbors. And the number of consistent values is 1 plus 1 plus 2, which is 4 here. 6 is larger than 4, so I'm going to try red in this case. So intuitively, why does this make sense? I want to choose a value that gives as much freedom as possible to its neighbors so that I don't kind of run into trouble and get things to be inconsistent here. And you can see that by having red here and red here, I have more options for the neighbors NT and SA. Then over here, since I can only do green here, and you can, if you look even one step ahead, you'll notice that this is already going to cause trouble. Okay, so least constrained value, order the values in order to free up the neighbors as much as possible. So this might seem a little bit strange. So most constrained variable, least constrained value, these seem superficially kind of at odds with each other. But there is a reasoning, which is that variables and values are very different. So in a CSP, every variable must be assigned. So we can't leave a variable alone and hope that the problem will disappear later. So what we're going to do is we're going to try to choose the most constrained variables as possible. So if we're going to fail, we're going to choose the hardest variables first to try, and we might as well fail early, which leads to more pruning. On the other hand, values are those that we're going to choose. We just need to choose some value for each variable. So what we're going to try to do is choose the value that is most likely to lead to a solution. It doesn't matter if some value is going to cause trouble, because if we choose a value that happens to work, then maybe we'll be happy. So when do these heuristics help kind of formulate? The most constrained variable is useful when some of the factors are constrained. It's okay if some of the factors are not constrained, but it's important that at least one of the factors is a constraint, which means that it's something that returns can return 0. If all the factors are returning non-zero values, then none of these heuristics are going to be helpful. You kind of have to explore everything. This constraint value is useful when all the factors are constraints. In other words, the assignment weights are 1 or 0. So they have to look like this, but not like this factor. And the rationale here is that we have to, we don't have to find all of the assignments in this case. If we find an assignment that has weight 1, then we know we're done, because 1 is the maximum weight possible, and we just return immediately and kind of stop early. But if there's other factors which have varying values, varying weights of different magnitudes, then we can't necessarily stop if we find a weight of 2. Well, maybe there's another assignment that has a weight of 4 or 8 or 17 or so on. We can't really stop early enough. And notice that we need forward checking to make both of these things work, because these heuristics rely on counting the number of elements in domains. And so we need to groom or prune these domains so that the heuristics are. Okay, so let's conclude here. So we presented backtracking search. So backtracking search has 3 choice points. First, we need to choose an unassigned variable, xi. This is done by using most constrained variable, MCV. Once we've found a variable to assign, we're going to order the values of that unassigned variable based on the LCV heuristic, or least constrained value. And then we're going to compute the updated weight, as we discussed before. And then we're going to update the domains via one-step lookahead, aka forward checking. And then if the number of elements in any domain is 0, then we stop there and don't recurse, otherwise we. Okay, so notice that none of these heuristics is guaranteed to speed up backtracking search. There's no theory here, but often in practice, these can make a big difference. So next time, we'll look at the look ahead and see how we can even improve upon forward checking. So that's it.